A 60 Hz 3-phase Y bus experiencing 5 to 8 volts alternating current with around 30 amps per phase presents a troubleshooting challenge. The stray voltage on the neutral line, despite the expectation that it should be shunted to ground via the transformer bonding, indicates a problem that requires systematic investigation. Here's a guide to potential sources and troubleshooting steps to address this issue. Firstly, loose neutrals can cause stray voltage. Check for loose or damaged neutral connections at the transformer, switchgear, or equipment. Secondly, unbalanced loads can also be a problem. Unequal load distribution across the 3 phases can create a voltage potential on the neutral. Thirdly, grounding issues can contribute to the problem. Poor grounding at the transformer or switchgear can prevent the voltage from being shunted to ground effectively. Fourthly, induced voltage can play a role. Current flowing through nearby conductors can induce voltage in the neutral line due to electromagnetic induction. Fifthly, capacitive coupling can be a factor. Capacitance between the neutral line and other conductors can create a voltage potential, especially in long runs or closely spaced conductors. To systematically address these potential sources, here are troubleshooting steps. Step 1 is to verify grounding. Check the grounding connections at the transformer, switchgear, and equipment using a continuity tester. Ensure that the grounding electrode system, consisting of rods or plates, is properly installed and connected, meeting the requirements of the National Electrical Code, or NEC. A low resistance path to ground is crucial. Step 2 is to inspect neutral connections. Carefully examine all neutral connections for tightness and integrity. Tighten any loose neutral connections and replace damaged neutral wires or terminals. Corrosion or physical damage can significantly increase resistance and contribute to voltage buildup. Step 3 is to balance loads. Redistribute loads evenly across the 3 phases to minimize unbalanced currents. Use an ammeter to measure the current in each phase and adjust the load distribution to achieve a balance as close as possible. Unbalanced loads force current to flow through the neutral, creating a voltage drop. Step 4 is to check induced voltage. Use a voltage meter, preferably a true root mean square or RMS meter, to measure the voltage between the neutral and other conductors in the vicinity. If induced voltage is present, consider shielding or rerouting the conductors to minimize electromagnetic interference. This is especially important if the neutral runs parallel to high current conductors. Step 5 concerns capacitive coupling. Install ferrite cores or capacitors to reduce capacitive coupling between the neutral line and other conductors. Ferrite cores can be clamped around the neutral conductor to increase impedance at higher frequencies, while capacitors can provide a low impedance path for capacitively coupled currents. Step 6 is to contact the utility. If the problem persists after implementing the above steps, contact the utility provider to investigate potential issues on their side, such as transformer grounding or system imbalances in the distribution network. Utility side problems can often manifest as voltage irregularities in the customer's neutral. When troubleshooting, keep these additional notes in mind. Use a digital multimeter to measure the voltage accurately, as analog meters may not be sensitive enough to detect the small voltage levels present. Digital multimeters offer higher resolution and accuracy, which is essential when dealing with stray voltages. Be cautious when working with stray voltage, as it can present a shock hazard. Always follow proper electrical safety procedures and wear appropriate personal protective equipment, including insulated gloves, safety glasses, and arc-rated clothing. Consider using a ground fault circuit interrupter, or GFCI, to protect yourself from electric shock. Ensure that all equipment is properly grounded to minimize the risk of electrical hazards. Verify the integrity of the grounding system by performing an impedance test. This test measures the resistance of the grounding path and confirms its ability to safely carry fault current. Refer to NEC section 250.4 for grounding requirements. Check the neutral to ground voltage at various points in the system. A significant voltage difference between neutral and ground indicates a problem with the grounding or neutral connections. The NEC specifies that the neutral to ground voltage should be as close to zero as possible. Investigate harmonic distortion. Harmonics can cause increased current flow in the neutral conductor, leading to voltage drops. Use a harmonic analyzer to measure the harmonic content of the current and voltage waveforms. Consider installing harmonic filters to reduce harmonic distortion. Review the load types connected to the system. Certain types of loads, such as variable frequency drives or VFD and electronic ballasts, can generate harmonic currents that contribute to neutral voltage. Adjust the settings of these devices to minimize harmonic generation or install appropriate filters. Inspect the transformer connections. Ensure that the transformer windings are properly connected in a Y configuration and that the neutral point is securely grounded. Loose or corroded connections can cause voltage imbalances and contribute to stray voltage. Check the transformer's nameplate for the correct voltage and current ratings to verify its suitability for the connected load. Examine the bonding jumpers. Verify that all metallic enclosures, raceways, and equipment are properly bonded to the grounding system. Bonding jumpers provide a low impedance path for fault currents and help to equalize voltage potentials. Refer to NEC section 250.92 for bonding requirements. Evaluate the proximity of other electrical systems. Nearby electrical systems such as high voltage power lines or industrial equipment can induce voltage in the neutral conductor. Maintain adequate separation between the neutral conductor and other electrical systems to minimize induced voltage. Shielding the neutral conductor can also help to reduce induced voltage. Measure the impedance of the neutral conductor. High impedance in the neutral conductor can cause voltage drops and contribute to stray voltage. Use an impedance meter to measure the impedance of the neutral conductor and compare it to the manufacturer's specifications. Replace the neutral conductor if it exhibits excessive impedance. Check the operation of surge protective devices or SPD. SPD protect electrical equipment from voltage surges, but they can also contribute to stray voltage if they are not properly installed or maintained. Verify that the SPD are correctly grounded and that their voltage ratings are appropriate for the system. Test the SPD periodically to ensure that they are functioning properly. Analyze the voltage and current waveforms using an oscilloscope. An oscilloscope can provide detailed information about the voltage and current waveforms, including distortion, noise, and transients. This information can help to identify the source of the stray voltage. Use the oscilloscope to measure the amplitude, frequency, and phase angle of the voltage and current waveforms. Consult with a qualified electrical engineer or electrician. If you are unable to resolve the problem yourself, consult with a qualified electrical engineer or electrician who has experience troubleshooting stray voltage issues. They can perform a thorough inspection of the electrical system and provide expert guidance. The cost of hiring a professional may be offset by the savings in time and resources, as well as the reduced risk of electrical hazards. Document all findings and actions taken. Keep a detailed record of all measurements, inspections, and repairs. This documentation can be helpful for future troubleshooting and maintenance. Include the date, time, location, and description of each activity, as well as the names of the individuals involved. Store the documentation in a safe and accessible location. Regularly inspect and maintain the electrical system. Perform regular inspections and maintenance to prevent stray voltage issues from recurring. This includes checking connections, tightening fasteners, cleaning components, and testing grounding systems. Implement a preventative maintenance program to ensure that the electrical system remains in good condition. Review the electrical system design. Ensure that the electrical system is designed in accordance with applicable codes and standards. The design should include adequate grounding, bonding, and overcurrent protection. If the electrical system is not properly designed, it may be necessary to make modifications to improve its performance and safety. Consider the impact of new equipment or loads. When adding new equipment or loads to the electrical system, consider their potential impact on stray voltage. Some equipment may generate harmonic currents or require special grounding arrangements. Consult with an electrical engineer to ensure that the new equipment is compatible with the existing electrical system. Evaluate the use of isolation transformers. Isolation transformers can be used to isolate sensitive equipment from the electrical system, reducing the risk of stray voltage. Isolation transformers provide a high degree of isolation between the primary and secondary windings, preventing the transfer of common mode noise and voltage. Consider using shielded cables. Shielded cables can help to reduce induced voltage and capacitive coupling. The shield provides a barrier against electromagnetic interference and helps to ground stray currents. Ensure that the shield is properly grounded to maximize its effectiveness. Implement a power quality monitoring system. A power quality monitoring system can continuously monitor the electrical system for voltage, current, harmonic distortion, and other parameters. This information can be used to identify and diagnose stray voltage issues in real time. The monitoring system can also provide alerts when abnormal conditions are detected. Educate personnel on stray voltage awareness. Train personnel on the causes and effects of stray voltage, as well as the procedures for reporting and addressing stray voltage issues. This can help to prevent accidents and ensure that stray voltage issues are promptly resolved. Provide personnel with the necessary tools and equipment to safely and effectively troubleshoot stray voltage problems. By systematically addressing these potential sources and following the troubleshooting steps outlined above, one can effectively identify and mitigate stray voltage issues on the 60 Hz 3-phase Y bus. Remember to prioritize safety and consult with qualified professionals when necessary. When checking the grounding connections at the transformer, switchgear, and equipment, use a continuity tester to ensure that there is a low resistance path to ground. The grounding electrode system should be properly installed and connected according to NEC requirements. Look for loose or corroded connections which can impede the flow of current to ground. Examine the grounding conductors for damage or deterioration, replacing them as needed. When inspecting neutral connections, pay close attention to the terminals and connectors. Tighten any loose connections to ensure secure electrical contact. Replace damaged or corroded wires and terminals to maintain a reliable neutral path. Use a torque wrench to tighten connections to the manufacturer's specified torque to prevent over-tightening or under-tightening. When balancing loads across the 3 phases, use an ammeter to measure the current in each phase. Redistribute loads as needed to achieve a balanced current flow. Consider using load balancing software to optimize load distribution. Monitor the neutral current to ensure that it is within acceptable limits. When checking for induced voltage, use a voltage meter to measure the voltage between the neutral and other conductors in the vicinity. Look for voltage fluctuations or spikes that may indicate induced voltage. Consider using shielded cables or rerouting conductors to minimize electromagnetic interference. Evaluate the proximity of other electrical systems that may be inducing voltage in the neutral conductor. When addressing capacitive coupling, consider installing ferrite cores or capacitors to reduce the coupling between the neutral line and other conductors. Ferrite cores can be clamped around the neutral conductor to increase impedance at higher frequencies. Capacitors can provide a low impedance path for capacitively coupled currents. Experiment with different types and values of capacitors to achieve the desired results. When contacting the utility provider, provide them with detailed information about the problem, including the voltage and current readings, the location of the affected equipment, and any troubleshooting steps that you have already taken. Cooperate with the utility provider to investigate potential issues on their side, such as transformer grounding or system imbalances in the distribution network. Follow the utility provider's recommendations for resolving the problem. When using a digital multimeter to measure voltage accurately, select the appropriate range and resolution for the measurement. Use a true or a miss meter to measure non-sinusoidal waveforms accurately. Verify the accuracy of the multimeter by calibrating it regularly. When working with stray voltage, always follow proper electrical safety procedures and wear appropriate personal protective equipment, including insulated gloves, safety glasses, and arc-rated clothing. Energize the equipment before working on it whenever possible. Use a ground fault circuit interrupter to protect yourself from electric shock. Be aware of the potential hazards of working with electricity and take precautions to avoid injury. Always assume that electrical circuits are energized until proven otherwise. By following these detailed guidelines, one can systematically troubleshoot and resolve stray voltage issues in a 60 Hz 3-phase Y-bus system, ensuring a safe and reliable electrical environment. Remember to document all findings and actions taken during the troubleshooting process for future reference and maintenance.